for it, feel free to come back. It will be downloaded after the meeting is finished. Okay. So can you see the screen? Abdullah Khalid, what do you mean? But هذا وشو? What do you mean? I didn't get your question.
What is this meeting?
This is a fluid mechanics tutorial. We will be solving some questions.
Okay.
Inshallah.
Okay, I must leave now because I have a quiz.
No problem. Then come back to the tutorial. It is recorded.
Okay, thank you.
Thank you. Okay, so let's start the first question here. Just let me crop it. Okay. So a glass manometer with oil as the working fluid is connected to an air duct as shown in the figure. Will the oil leaves in the manometer be as in figure A or B? What would your response be if the flow direction is reversed? So we have an oil flow here, oil, and there is a fluid here to measure the pressure difference or the height difference. Okay, so before we start, we need to remember Bernoulli equation. Bernoulli equation is simply three terms: the static pressure, P, plus half rho V squared, the dynamic pressure, plus rho G Z, the hydrostatic pressure. And it's only applied when certain conditions are met. What's the first one? The flow should be inviscid. The second one, the flow should be steady. Inviscid means the frictional forces are negligible. Okay, and steady means that the flow does not change with time. The properties, the pressure, anything does not change with time. Okay, and the third one is that the flow should be incompressible. Incompressible. Okay, what does incompressible mean? Mean that the density of the fluid does not change as we go in the duct or in the pipe. Okay, so the density here is the same as the density here, the same as the density everywhere. This is what incompressible mean. And the last one, it should be applied along a streamline. So if we have this flow, we have this streamline, we can apply Bernoulli equation between any 2 points in the streamline. Okay, those are the 4 conditions. You need to keep them in your mind. So given those, let's go back to the question. We have this oil flow. And let us apply Bernoulli equation between this point, which is directly above this end of the manometer, and this point here. Okay, we don't have number here to substitute. We will just look at the question here. Here the area is higher, right? The cross-sectional area is higher compared to the area here, right? Or here, the same thing. And if the cross-sectional area is higher, you know that the velocity will be lower, right? Because you have the volumetric flow rate, Q, or I think you call it here V dot in this course, V dot or Q, okay? V dot is equal the cross-sectional area multiplied by the velocity. So here I have a higher area, then I have lower velocity. And if I have lower velocity here, what will happen to the pressure? I will have higher pressure here because the mechanical energy is conserved. If I've applied Bernoulli equation between this point and this point, I have P1 plus half rho V1 squared, assume this is 0.1 and this is 0.2, is equal to P2 plus half rho V2 squared. So we said that the velocity at 0.1 is lower because the area is higher. And if the velocity is lower, then in order to compensate for this reduction in this dynamic pressure, then the pressure should be higher. So to make it a shortcut, just say if the area is higher, then the pressure will be, of course, higher. And of course, here I neglected this term because they are at the same level. Okay, so it will cancel from both sides. And the mechanical energy is conserved. Okay, the pressure at 0.1 is larger at the pressure at 0.2. Okay, this is the conclusion. Now, if you want to go in the vertical direction, remember we can go in the vertical direction, and the relation that will be applied is the relation that you took it in static fluid, that the P is equal P naught plus the density rho G H. This can be applied if you have straight streamlines and you want to go in the direction perpendicular to that. Okay, so if we have here P1, I will go down. Because I'm going down, I'm adding more weight of the fluid, then I will add rho GH. I will add this rho of the oil, the fluid here is oil, multiplied by G multiplied by this distance H. Okay, I will have the pressure here. Call it P1 star, okay? P1 star, which is equal to P1 plus rho of the oil, G H1. Okay, and here you have P2. P2, add for it H2, this one, H2. Then I will have here P2 prime. Okay, so P2 prime is equal to P2 plus rho of the oil, G H2. Okay, so we said that the pressure P1 is higher, right? And also H1 is higher than H2. So in total, P1 prime will be larger than P2 prime. The pressure here is larger than the pressure here. And then go another distance, by another distance, go to this point. I want to see the pressure here. And also I want to see the pressure here. So I will add, for those terms, I will add plus rho, but here there is an air. And I'm going down, so I will add also plus rho of the air multiplied by G multiplied by this distance H here. Let's name it H3 maybe here and name it H4. But at the end of the day, still you can neglect this term. Why? Because the density of the air is pretty much low. So you can just ignore it. We only care about the densities of the liquid that are present here. So I included this one because there is an oil here. But this is air, so just neglect it. And you can say that this P1 prime, which is here, is also equal to P1 prime here. And P2 prime, which is here, is also equal to the pressure here. Okay, now we reach to the conclusion that P1 prime is greater than P2 prime. And this is P1 prime here. And this is P2 prime. Now, if P1 prime is higher, then it should push the fluid and it should go up here because P2, it's like a scale, If the pressure here is higher, then it will push the fluid to a lower level and the fluid will rise here at the point of the lower pressure. Okay, so this means that this configuration is correct because here it goes down at the area of at the region of the higher pressure and it goes up here at the region of the lower pressure, and this configuration will be wrong. Okay, And if you reverse the direction of the flow, nothing will happen. Also the same conclusion, because it doesn't matter, because if the fluid is going from this direction, from this end, from the second end to this end, the area is still the same here. The pressure will be the same here and here. Nothing will change if you reverse the direction of the flow. Okay? Is it clear, this question? Okay. If you have any doubts, you can stop me, no problem. You can interrupt me anytime if you have anything not clear. Okay, let's go and solve another question. Okay, let's check this one. Okay, an airplane is flying at an altitude of 10,500 meter. Determine the gauge pressure at the stagnation point on the nose of the plane if the speed of the plane is 450 kilometer per hour. How would you solve this problem if the speed were 1050 kilometer per hour? Okay, so let's analyze this question. We have here an airplane. I'll just assume it look this way. Okay, those are the wings. Okay, and the air is blowing this way. Actually, the plane is moving. The plane is moving at a speed of 450 kilometer per hour. Now, from you know the concept of relative velocity. If the plane is moving at this to the right, and there is an air here, as if like the air is moving, is blowing at the plane at a velocity of 450. So the same thing. Now at this point, at the nose of the plane, the air will come to a complete stop because it will be blocked here completely. So here I will have the stagnation point. Stagnation. Stagnation means the velocity equals to 0, because here it will be completely blocked and then it will start to move this way and this way. But at this point, the velocity will be 0. Okay, and at the free stream line, here the velocity is 450. Again, this is relative. The plane is moving, but from the plane perspective, the air is blowing at a velocity of 450. So if you want to apply, what do we call it, the Bernoulli equation, okay, we have assume I will apply it along this streamline, and I will apply it between a point here in the free streamline and the stagnation point. So assume this is 1 and this is 2. So you have P1 plus half density of the air, V1 squared, and I will neglect the term of rho gz because they are at the same elevation. Whenever the 2 points are at the same elevation, you can just neglect the third term, which is the hydrostatic pressure, is equal to P stagnation. Okay, and the velocity is 0, so this term will be cancelled from here, and the last term will be cancelled from both sides. Okay, so this is what is required from the question, the stagnation pressure. Okay, I have the velocity, I have the free stream velocity, which is 450, and what's also given, I have the attitude of the airplane, and you can find the density at that attitude. Okay, if you just go to Google or anywhere, maybe in the appendix, you can find the density of the air at that attitude. Okay, and the pressure Yes, the pressure is the atmospheric. Okay, because we are at the atmosphere. So the pressure at point 1 will be the atmospheric pressure. So we have P stagnation is equal to the atmospheric pressure, P ATM, which is equal to 101,325 Pascal. Okay, plus half, and the density, I'm not sure at that elevation how much the density, but you can check it in the internet. Assume it's 1.2. Okay, this is 1.2 at the sea level, I think, but at that elevation you can find it, and if that question came at the exam, the doctor will provide you with that density. Okay, and then the velocity, convert it from kilometer per hour to meter per second. So 4 multiplied by 1,000 to convert from kilometer to meter, and divide by 3,600 squared. Okay, you can find the stagnation pressure. But here there is one problem. Let's calculate the velocity here when we convert it from kilometer per hour to meter per second. Just let me calculate it. It's 125 meter per second. This will cause a problem. What's the problem here? Because we applied Bernoulli equation, here, and when we apply Bernoulli equation, as if we said that the flow is steady, the flow is inviscid, we applied along a streamline, and the flow is incompressible. Correct? You remember the conditions. So as if I said that the flow is incompressible. But here we have the fluid is an air, and air is generally is compressible. Air is compressible. Okay, because if you have a piston cylinder and you have an air here, you can compress it freely, right? You can move this piston to here. You can compress the air at the compartment, right? So the air itself is compressible, but the flow of the air, when the air is at motion, the flow itself can be either compressible, or incompressible. How can I know that? If the flow of the air is compressible or incompressible. If you have water, water is incompressible fluid. If you have water here, you can maybe barely move the piston, like barely millimeters here, to compress the water. So it's in general, we say water is incompressible, and therefore the flow of the water will always be incompressible. But air is compressible, and if it's compressible, then the flow will be either compressible or incompressible. How can I differentiate? There is a relation that say, you remember Mach number, which is equal to the velocity of the fluid divided by the velocity of sound. Okay, if Mach number is less than 0.3, we can assume the flow of the air as incompressible, and then I can apply Bernoulli equation. But if Mach number is greater than 0.3, the flow in that case will be compressible, and applying Bernoulli equation is not justified. So here, if you calculate Mach number 125 divided by the velocity of sound, approximately 300, what's the answer? 125 divided by, you have 0.4. Okay, which means that we are in this case where the flow is compressible and we cannot apply Bernoulli equation. But why I applied it here? Because I don't have another tool to apply. You just now learned Bernoulli equation, and if you learned another equation, there is another equation that consider the compressibility of the flow, there are another terms and you will get different equations, and then at that case you can apply it. But now in your case you only took Bernoulli equation, so you have no choice, just apply this equation and you will have certain error. You just have to accept it. Okay, clear this question? Or yes, Muhammad, do we check one? Yes, what's your question? The gauge pressure. An airplane is flying an altitude of determine the gauge pressure at the stagnation point. Okay, so you need to subtract the atmospheric pressure from both sides. So the stagnation pressure here, thank you for wearing me, this from here and from here also, minus PATM. Then you have plus P1, and P1 is equal to the atmospheric, so you just cancel this one. Okay. Yes. P stagnation minus PATM. Okay. Okay. Any questions? Fatma, Ismail. Okay. Okay, so let's move on to another question. We have here this question. Okay, water at 20 degrees Celsius is siphoned from a reservoir. Okay, this is the reservoir, and we are sucking some water, and we want to supply it to a certain region. For D is equal 8 centimeter. This is the diameter of this cross section, and D capital is equal to 16 centimeter, the diameter of the larger cross section. Determine A, the minimum flow rate that can be achieved without cavitation occurring in the piping system. Now, before we solve this question, do you know what's cavitation? Did you do the fluid lab experiment related to cavitation? Okay, so you know what's cavitation. Cavitation is simply when the pressure in the pipe anywhere drops, the pressure in the pipe at a certain region, maybe this point, maybe this point, drops below the saturation pressure, Psat, at the temperature given in the question. Okay, so here what's the temperature? It's 20 degrees Celsius. There is a corresponding saturation pressure if you took thermodynamics, I'm not sure. If you took it, then you know how to find it, right, in the appendix. And if you didn't take thermo, then I will just show you how. Go to the appendix here. You have the book, right? Go to appendix 1, property tables. Then go to A3. You have here the temperature, you have the saturation pressure. So our temperature is 20. What's the corresponding saturation pressure? Is 2.339. Okay, so I'll just write it here because we will use it later. 2.339 kilo Pascal. Okay. If you know the phase diagram of water, we have this is the temperature and this is the pressure. We have something like this. Something like this, where this region is solid. I think, and this region is liquid, and this is the gaseous region. So this pressure is actually this line. You see this line? This line. So at a given temperature, at a given values of the temperature, from this point until here, we have certain value of the pressure, certain corresponding values of the pressure, which are the saturation pressure. Okay, and whenever the liquid, we are here in the pipe, we are in the liquid region. Whenever the pressure suddenly drop below that pressure here, then cavitation will occur. We'll have the gaseous phase and cavitation will occur. This is simply cavitation. So now anyhow, let's just start solving the question. So in order to solve this question, I need to determine first where cavitation will occur. Where cavitation will most probably occur in this piping system. Okay, so cavitation is simply when the pressure drops very sharply down. So I can here, we can draw a rough graph of the pressure distribution. So if you apply Bernoulli equation between point 1 and any point here, okay, let's apply it, for example, at this section where the diameter is equal to d small. You will see that the pressure, okay, the pressure will drop something like this, okay, because here the no, sorry, the pressure will go here. The pressure will be constant, okay, and then the pressure here will start to drop. Okay, why is that? Because this region has a higher elevation, and if you apply Bernoulli equation between point 1 and point 2, whenever you increase the elevation, then what will then the pressure will decrease, the static pressure, because here you have what? You have P1, P1, and then there's no velocity here. The fluid is stagnant here, and then the elevation is 5 plus rho g z. Okay, and here, if you apply it at any point here, what you have? You have the pressure P2 plus half rho V2 squared plus rho gz. Now in this section, the velocity is constant, right? Because we have the same cross-sectional area. Q is equal VA. The volumetric flow rate is constant in the system, and then if the area is constant, then the velocity will be constant, no matter if the orientation differs, okay? So this term, I have nothing to do with it. Just look at this one and this one. Whenever I increase the elevation, of the point, the pressure will decrease. So that's why I draw the pressure profile this way. Here it is the same elevation, so the pressure will not change. Then here, as I'm going straight up, or sorry, inclinedly I'm going up, I'm adding Z. The Z of the point will increase, and therefore the pressure will decrease. So that's why I dropped this line this way. Okay. Then at this, the second cross section where the emitter is equal to D capital, how the pressure profile will look like. First here at the interface here, I have an increase in the area, right? I have a sudden increase in the area. What will this cause? If the area increase, what will happen? If the area increase suddenly, the velocity will decrease. Yes, the velocity will decrease. And when the velocity decrease, what will happen? Here, remember at the interface here, I'm looking at the interface from the right and from the left. So the elevation is constant, right? So here we have again P1. P1 and it's stagnant, okay, and plus rho gz at point 1. Now here at the interface, I have the same elevation, rho gz, and I have the same sorry, also only I have the same elevation. So now I have pressure and the pressure term and the dynamic pressure term, V squared. So look at those. When I go from the left side of the interface to the right side, I'm increasing the cross-sectional area, and therefore the velocity will decrease. Now, when the velocity decrease here, the pressure will increase to compensate for this reduction. And I'm not changing this elevation because I'm just to the left and I'm just to the right of this interface. They are both at 2 meters above the ground. Okay, so this will I can conclude that whenever the area is bigger, I have a bigger pressure. So here at this point, I'll have a jump in the pressure. A jump in the value of the pressure. Let's say till here. Okay, and now the same principle will apply as we were here. Whenever we're adding more elevation, the pressure will drop, drop until we reach here the minimum. And then we are decreasing the elevation, then the pressure will continue increasing. Okay, so this is somehow the pressure profile. Now, from this pressure profile, what are the critical points where the pressure could be minimum, possibly could be minimum? I have either this point or this point, right? Maybe this one is lower than this one, and in that case, this will be the critical point where cavitation will occur, because cavitation is the lowest pressure in the system. Okay, or either I have this point is the lower pressure region if the graph is like down this way. Okay, and the point was here, then at that case, point 3 will be the critical point where cavitation will occur. So how to know which one, 2 or 3 is the critical point? I need to apply Bernoulli equation. Okay, let's apply Bernoulli equation. Let's apply Bernoulli equation between point 1 and point 3 and see what will happen. We have P1, the atmospheric, right? He gave you this simple mean atmospheric, and plus rho G Z1 is equal to, at point 3, we have the pressure. Assume that stagnation will happen at 3. So here I will, sorry, not stagnation, cavitation. Maybe I was saying stagnation for the whole time. I'm not sure. Sorry for that. I mean cavitation. P cavitation. Okay, at point 3 plus half rho V3 squared plus rho GZ3. Now substitute this value, assuming that cavitation will happen at point 3, and calculate the velocity. So here I have the atmospheric pressure, 325, plus the density of water is approximately, it's water, right? It's water, yes. The density of water is approximately 100 multiplied by the gravitational acceleration 9.81. The elevation at point 1, 1 plus 4 is 5. Okay, assuming this is my datum or my reference. You can take it wherever you want. Is equal to the cavitation pressure. Now this is in kilopascal. Remember here I put the pressure as in Pascal, because this is in Pascal and this will be in Pascal. So I need to convert this one to Pascal. So just remove shift the dot 3 to the right. So we have 2,339 Pascal plus half thousand V3 squared plus 1,000 9.81 and then you have Z3 is equal to 7. So V3 is equal to, let me calculate it first. Okay, 12.6 meter per second. Okay, now this velocity is when the cavitation, assume that cavitation will occur at 0.3. I will have cavitation because I substituted the cavitation pressure. Or just like I'm on the verge, because this is the line of P cavitation, and just if the pressure drop below this pressure directly, then cavitation will occur. So I'm at the verge, okay? So now I have A3 multiplied by V3, and I have A at 0.2, the second critical point, this one, okay? A2 multiplied by V2. I'm applying here the continuity equation, which is V equal V, okay? A3, I have the diameter, so it's by d squared to the power, d squared over 4. What's the diameter at 3? 16. 16 means 0.16 meter squared divided by 4, multiplied by this velocity, 12.6, is equal to the diameter at 0.2. Sorry, the area at 0.2, which is pi. The diameter is 8, 0.08 meter squared divided by 4, multiplied by V2. Now what's V2? Remember, still we are not sure if the cavitation will occur here. I assume that cavitation will occur here. And now I want to confirm that. I'll show you how I'll confirm. So let's just calculate V2. You have pi 0.16 squared divided by 4 times 12.6 equal to pi 0.08 squared divided by 4 x. So you have V2 accordingly is 50.4 meter per second. Now, what I will do, I will apply now Bernoulli equation between 0.1 and 0.2, substituting this value of the velocity, and I want to find what P2 will equal to. If it turns out that P2 is higher than P3, which is the stagnation pressure, that means, yes, P3 has a lower pressure than P2, and cavitation will most probably occur here, okay? But if P2 turns out to be lower than P3, then in that case, location 2 is the location that is more susceptible to lower values of the pressure, and therefore cavitation is more likely will occur at 0.2. Okay, so this is how you will check. So the same equation, apply the same equation here, but now we want to find the pressure. The pressure is unknown, and I have the velocity. So let me just apply it here. I won't write it again. You just write it here. You will substitute V2 here, and you will make P as an unknown. Find it. Okay, so P2 will equal to, when I substitute, And also the elevation is different, right? Because 0.2, the elevation is 2, not 7. So you need to be careful. Plus multiplied by 2. So this is the result. I obtained a negative value of the pressure, 113.325. I obtained this pressure. What does that mean? That means 0.2 is the point which is associated with the lower value of the pressure. Therefore, I need to repeat the calculation. I need to repeat the calculation from the beginning. And now I'm sure that 0.2 is the point that's associated with the lower pressure, and therefore cavitation will occur there if I applied this pressure here. So you need to understand that the 0.2 where the lower pressure will occur. And in case the pressure here drop below that, then cavitation will occur at 0.2. So now I will repeat the same. I did this intentionally. I assumed first 0.3 where the cavitation will occur, though I know it will occur here, but just to show you how the procedures will go. Okay. So now I'll repeat the calculation applying Bernoulli equation between 0.1 and 0.2 where cavitation is here, cavitation. Okay, so you have P1 plus half rho, sorry, we don't have, the fluid is not moving at 0.1, we just have plus rho G Z1 is equal to P cavitation at 0.2 plus half rho V2 squared plus rho GZ. I want to find V2, and then when you find V2 multiplied by the area, you will find the volumetric flow rate of the system that will just give me cavitation. Okay, because this is what is required from the question. What's the flow rate? The minimum flow rate that will achieve, that can be achieved without cavitation. I'm on the verge. Okay, again, I'm on the verge. So P1 is the atmospheric plus 1000, 9.81, Z1 is 5, is equal to the cavitation pressure 2339 or 2339, yes, plus half 1000. V2 squared is unknown, plus 1000, 9.81, and Z2 is 2 meters. Okay, find V2. Okay, it's 16.02. Find Q, which is V2 multiplied by A2. In case we have cavitation, so 16.02 multiplied by the diameter at 0.2 is 8 centimeter. 8 squared divided by 4. 0.0805 meter cubed per second. Okay, clear? Or you want me to repeat something? If there's something not clear, I can repeat it, no problem. Sure, everything is clear? تمام. If it's not that clear, you can again watch the recording, and if there's something not clear, you can contact me in MS Teams or email or whatever. Okay. So we have also the second part. Now, assume that I have applied this volumetric flow rate that I just found, Q. Assume that now I apply it in the system. Now, what is the maximum elevation of the maximum elevation of the height of the highest point of the piping system to avoid cavitation? Okay, so assume that now I will just elevate this point to a further distance. Okay. I'll just keep rising it till this point become the critical point. Okay. We remember from our calculation, we found that with this configuration, the point 2 is the critical point where the pressure will be the minimal. Okay, but now assume that I'm rising this point, I'm rising it to a distance h until this point become the point where cavitation will occur. And you are applying the same volumetric flow rate that were causing cavitation here. Okay, it's not causing cavitation, it's about to cause cavitation. And now this is your variable till where you can raise this point, because when you raise it, the pressure will keep dropping, will keep dropping until you have cavitation. So what's this height? Okay, again, we can apply Bernoulli equation. We have V1 plus half rho. Oh, I keep writing this term. There's no velocity at point 1. Sorry. V1 plus rho G Z1 is equal to P3 plus half rho V3 squared plus rho G Z3. Okay. Now you have the velocity. You have the velocity from the, where did we calculate it? Oh no, we didn't calculate. We have V2. Okay. We have V2. We can apply the continuity equation because, as I said, assume you are applying the same volumetric flow rate. So you have the velocity and you have the area at point 2. You can find the volumetric flow rate that we just find it here, and divide this volumetric flow rate by A3 to find V3. Okay, and then substitute it here, V3, and substitute P as the stagnation pressure, because assuming that we will keep raising this point until it becomes the critical point where the cavitation will occur. And this is Z3. Z3, you have it in the question. Sorry, Z3, this is the variable that we want to find. What's the elevation of this point so that cavitation will occur, applying the same volumetric flow rate in the previous section, in the previous question, or the section A. Okay, so you have here again the atmospheric pressure plus rho 1000 G 9.81, Z1 is 5, is equal to the cavitation pressure plus half 1000, and then you have V3. V3 is equal to the volumetric flow rate 0.085 divided by the area by D, which is 0.16 squared over 4, and this is the whole term is squared, plus rho G and Z. So just plug this equation in the calculator and find Z1. we'll find the at this case, both this point and this point cavitation can occur, because once I substituted the assumed that cavitation will occur here when this point, when the point 3 was at this elevation. But when I rise it up and substitute the cavitation pressure here, then cavitation may occur either here or in both. Okay. Okay. Clear? Part 2. Yes, that's correct. 14.27. This is the correct answer. Z1 is equal 14.27. Okay, we'll just solve another question because we don't have that much time, and maybe I can record for you the remaining questions. Okay, because it's already 5. What else we have? Okay, so let's solve this question. This is also related to cavitation, or let's solve this one. Okay, let's solve. This is also, I think, in your homework. Okay, so air, again, we have air. We need to check for the compressibility condition. Okay. Just a minute. Okay, so you have airflow through a pipe at a rate of 120 liter per second. The pipe consists of 2 sections of diameter 22 centimeter and 10 centimeter, with a smooth reducing section that can connect them. This one. Okay, the pressure, the pressure difference between the 2 pipe sections is measured by a water manometer. This one, there's a water here. Neglecting frictional effect, determine the differential height of water between the 2 pipe sections. This, want to find this H. Okay. Take the density of air as 1.2. If you have anything, you can leave, no problem. And if you don't have, just stay with me a few seconds until we solve this question. Okay, and it's recorded, no problem. If you have anything, you can leave, no problem. So here, again, here we have air, right? So before we apply Bernoulli equation, we need to make sure that the flow is incompressible. Okay, but as you can see here, when he gave you one value of the density, then most probably he is like he's saying for you it's incompressible flow, and just use this value, because you know, if the flow is compressible, then we have a value of density here and a value of density here, different values, and we cannot apply Bernoulli principle. Okay, but when he gave you only one value, then he's telling you indirectly that this flow is incompressible and you are okay to use Bernoulli equation. But now let's double check to make sure. Okay, we have here Q is 120, or V dot or Q. Okay, V dot or Q is equal 120 liter per second. If we want to convert it to meter cube per second, what we will do, we have 1 liter. 1 liter is equal to or the opposite, no, 1 meter cubed. 1 meter cubes is equal to 1,000 liter, right? 1 meter cubes is equal to 1,000 liters. So if I want to convert from liter to meter cube, I need to divide by 1,000. So 1, 2, 3. So you have 0.12 meter cubed per second. Okay, and you have this cross-sectional area. For example, let's consider the worst case scenario. Where is the higher velocity? Where at 1 or 2, where the velocity will be higher? Of course at 2, because you have lower cross-sectional area, then you have a higher velocity. So we will check Mach number at this point. Okay, because this is the higher velocity, the higher the velocity. If the higher velocity meet the condition of Mach number, then of course the lower one will also meet, because Mach number should be less than 0.3. And if you have here the velocity, the greatest velocity divided by the velocity of sound meet this condition, then of course the lower velocity at that section will also be less than 0.3. All right, so we'll just take the section associated with the higher velocity. So you have the velocity is equal to Q divided by A. So you have 0.12 divided by the diameter is 0.1, okay, meter divided by 4. What's the velocity? 0.12 divided by 0.1 squared over 4. You have 15.27 meter per second. If you divide this one by the velocity of sound, which is approximately 300, you have how much? You have 0.05, which is less than 0.3. Okay, so of course the flow is incompressible and you can apply Bernoulli equation. Remember, Mach number to be 0.3, the velocity of the air should be approximately 100. Okay, so whenever you have a velocity of air less than 100, then the flow is incompressible. Okay, so now we are okay to use Bernoulli principle. So you have P1 plus half rho V1 squared is equal to P2 plus half rho V2 squared. Okay, and I cancelled both terms from the hydrostatic pressure because they are at the same elevation. Assume I will apply Bernoulli equation along this streamline. Okay, you have this point here and this point here. They are at the same elevation. For example, assume my reference is here. So they are at the same elevation. So you just can drop the last term of Bernoulli equation from both sides of the equation. Okay. Now we will rearrange the equation because he wants the pressure, the height difference. He wants the height difference, not the pressure difference. So I will just bring one pressure to I will bring this pressure to the other side, and I will bring this term to the other side. So you have P1 minus P2 is equal to half rho V2 squared minus half rho V1 squared. Okay. V2 and V1 you can find it easily applying the continuity equation because we just found the V2. This is V2, and also apply it once again to find the V1. V1 is equal to 0.12 divided by pi. The diameter at point 1 is 22 centi, meaning that it's 0.22 meter divided by 4. This is the area at the denominator. This is the area, cross-sectional area, and this is the flow rate. So it's equal to 0.12 divided by 0.22 squared over 4. You have 3.15 meter per second. Okay. Now the problem is here, P1 minus P2. I want to find the height. Now I will apply the the relation when we go in the normal direction, in the perpendicular direction to the streamline. So at this point we have P1, just as the first question we solved. Okay, when I go here, okay, I should add P1 plus rho of the air. This is air here, G H, because I'm adding more weight, so I need to add the what I made here, P1 plus rho GHS is equal to the pressure here. Call it P1 star, okay? P1 star. Now, because the density of air is very small, we can just neglect this term. So P1 here is the same as P1 here. And also, if you go down until you hit the surface of the water, still you have P1, because again, the density of air is very small. Even though if you go that much height from here to here, you need to add rho air, okay, G H, but at the end of the day, the density of air is like very small, so you can just neglect it and assume that P1 here is the same as P1 here. Okay, and the same principle applied to the other direction. P2 here is equal to P2 here. Now from this we can develop an we can rewrite this equation, because here, if you have P2 here, now let's solve just like you learned in the chapter, maybe in chapter 2 or 1, I don't remember. You took the manometer relation, how to go through the manometer and develop pressure relations, right? So assume I will start from here. I have P2, right? Then I will go down. I need to add, right? Because more weight of the fluid is now above me, so I need to add pressure. Plus rho of the water, G H. I reach this point, and whenever the 2 points are at the same level, then you have the same pressure in the manometer. So here this is P1, meaning that this is also P1. So P2 plus rho water GH is equal to P1. Okay, and what I have here, I have P1 minus P2. So rearrange this equation, bring P2 to the other side. So we'll have P1 minus P2 is equal to rho water GH. So just remove this one and put rho water GH is equal to the right hand side. Take half rho as a common factor. Half rho. This is air. Okay, don't mix between rho here and rho here. This is the working fluid on the duct, but here this is the fluid on the manometer. So half rho air, take it as a common factor. You have V2 squared minus V1 squared. Okay, substitute both. Rho of water is 100. G is 9.81. H is unknown, is equal to half. The density of air he gave you, the density in the question, 1.2. 1.2 V2 squared. What's this number? I cannot read it. 0.05. What's this? I don't know what's this. I don't remember. No problem. Just substitute the Q, the volumetric flow rate that is given, divided by A2 squared, okay, minus the volumetric flow rate divided by A1 squared. Okay, you have Q in the question, which is 120 liter per second, and you have the diameters. You can find the areas, and you have one unknown in the question. Find H is equal to 1.37 centimeter. Clear? Any questions? You are welcome. Please, if you have anything, just watch the recording, and if there's any question, just come back to me. And thank you all for, I hope I didn't take much of your time. we exceeded the time of the tutorial. Forgive me for that, and inshallah we'll see you after the spring break, inshallah. Maybe we will reset the day of the tutorial depending on those who did not vote. If they vote, maybe we can change the day of the tutorial, and if not, it will be repeated every Monday, inshallah. So that was it, and assalamu alaikum.